Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on August 17, 2025, about 5 days ago. The headline is bold. An automated machine learning pipeline predicts manufacturing unit costs straight from two-dimensional engineering drawings, hitting around 10%, mean absolute percentage error, across diverse part groups. The paper is titled, Machine Learning-Based Manufacturing Cost Prediction from 2D Engineering Drawings via Geometric Features. And as we will see later, the practical payoff is compelling. In short, the approach parses raw drawing geometry and materials, learns cost patterns per product group, and provides explainable drivers that speed up quotation workflows. Building on that, one highlighted post summarizes the core idea, predicting manufacturing costs straight from 2D CAD drawings using XGBoost on geometric features. The post includes a paper snapshot and earns about 290 likes, which signals solid engagement for a technical topic. We are looking at an example two-dimensional engineering drawing that the pipeline parses to extract geometry and dimensions. The full sheet shows multiple orthographic views with detailed annotations, which provide the rotated and radial dimensions that later drive cost features. You can see callouts, tolerances, and material notes near the title blocks, so the parser can capture text tags alongside shapes. Overall, this illustrates the raw CAD richness that enables precise feature statistics rather than noisy image cues. Now we are looking at a montage of 6 representative drawings, which illustrates the dataset breadth across major product groups and shows how many DWG files each group contributes. You can see inner tie rod end, control arms, wishbones, ball joint, and link stabilizer, so the parser confronts diverse geometries and annotation styles. This variety matters because the learned cost features must generalize across shapes, dimensions, and title block formats. The counts beneath each panel hint at class balance that influences model accuracy. Here we are looking at the parsing reference table, which lists each geometric entity and the properties the pipeline extracts, so you can see exactly what feeds the features. The entries cover line, circle, arc, spline, and ellipse. For lines, the system records start point, end point, and length, while circles keep center point and radius. Arcs add start and end angles, splines include control and fit points with degree, and ellipses store major and minor axes. We are looking at the results table that compares mean absolute error and mean absolute percent error across product groups for XGBoost, CatBoost, and LightGBM. You can see sizes ranging from a few dozen to over 1,000 drawings, which helps explain why accuracy varies. Several rows fall below 10%, including tie rod assembly at about 5% and wishbones near 11%. Notably, CatBoost leads for several complex housings, while XGBoost often wins on assemblies with clearer geometric patterns. Now we are looking at a scatter of predicted cost versus actual cost, which summarizes performance across every product group. You can see a dense green band tracking the black dashed diagonal, so predictions align closely with reality over thousands of drawings. The spread widens at higher actual costs, and those points tend to fall below the diagonal, which indicates underestimation for expensive parts. Overall, the diagonal hugging pattern reinforces the roughly 10% error we discussed earlier. Wrapping up, the key gains are clear. Geometry alone can deliver reliable cost estimates, roughly 10% error on average, and the explanations pinpoint what drives price, like rotated dimension maxima and arc statistics. Gradient-boosted decision trees, meaning ensembles of small split trees trained sequentially, make this practical. Thanks for tuning in. I am Alex. See you next time.